Yeah, so as I was saying, the solar mass black holes that come from either small PBH or a dark matter accumulation eating a neutron star, they should follow the neutron star mass distribution. So by just looking at this distribution, you can see that a candidate observed, let's say, at 2.6 solar mass is highly disfavored. And so doing such a simple statistical test on distribution already allows you to make powerful statements that large solar mass black holes are very unlikely to come from either small PBH or particle dark matter eating neutron stars. And of course, this also suggests that further understanding of stellar evolution, in particular, where's the mass gap and things like this, is very important. So more work is to be done. Now, so far we have discussed the small black holes and the solar mass black holes, but what about the bigger ones, the intermediate mass black holes? Well, are they primordial? So very recently, LIGO also detected the first intermediate mass for the 150 solar mass black hole. And in this study, the first author is the student who is supervising this, we proposed a new general PBH observable to understand this. And this is based on the fact that a black hole flying through the interstellar medium will interact with the gas and deposit energy. And there's various channels of interaction. In particular, you'll have dynamical friction, which is basically gravity drag with formation of accretion disk. You'll have some photon emission. There can also be some outflows and baryonic winds, so you can have some proton emission. But basically, these are all different ways how you interact with surrounding gas and deposit energy. And so then the gas will be a little bit heated. And then you can ask, well, how is my heating versus cooling balance spoiled, and place constraints this way? And turns out, in fact, if you pick a sufficiently favorable system, such as the LEO-T, you can cover a quite wide variety of black holes and a sizable parameter space. In particular, black holes are relevant for LIGO. So that, of course, is interesting. Now, I have so far discussed the various astrophysical signatures and how PBH can solve some astronomy puzzles, but I have not discussed where do they come from. So where did PBH come from? Of course, there's many formation models, but let me present to you one interesting possibility of primordial black holes from scalar fragments. And this was originally suggested by Alex Fusenko, a student, and then I introduced some other variations of this mechanism. Then with Sasaki-san, we understood this in more generality. And the basic idea here is that scalars, of course, are very generic in BSM models, especially in models of SUSY, where you have many flat directions. And post-inflation, if you have self-interactions, then the scalars could fragment, meaning break apart, from instabilities into pieces. And these pieces would be either cuboles for a complex field or oscillons for real field. And in fact, if gravity turns out to be the weakest force, as suggested by some top-down, more fundamental theory arguments, then it could be possible the fragmentation is actually more generic than previously thought. Now, and the basic idea is that you have some condensate, and then you run your time, and you see there is some stable fragments. And how can now form your PBH? Well, if you have some, since this whole process is stochastic, so sort of random, if you have some very lucky region where you have some very big overdensity, maybe it's possible to collapse to PBH. So this is basically the idea. And the interesting thing about this proposal is that the collapse from this overdense region is unrelated to any inflationary type of perturbation, so you do not need to worry about the fine-tuning of this mechanism and the relationship to the CMB and things like this. So it's totally unrelated to inflationary perturbations. This is an interesting point about this. And then, depending on the various model parameters, you can make PBH in different regions. And for some very generic numerology parameters, you can make PBH based on some interesting low-scale SUSY scalars. But one interesting feature that I would like to highlight about this possibility is that you can make with this mechanism black holes with a high spin. So in usual formation mechanisms, this is not so easy, but here the basic argument is that, well, a lot of the pieces are flying together, and each piece has some angular momentum. So actually, it is likely that such scenario results in black holes with big spin. So that is an interesting feature. Now, another, and this is a whole class of scenarios. Now, another interesting scenario that I would like to tell you about is the black holes from bubble multiverse. And this is a generic mechanism for making PBHs broadly distributed in mass. So before we saw that the previous mechanism yields a peaked mass distribution, but a big spin possible. But this is a mechanism how to make black holes broadly distributed in mass. And a lot of important work is done by Alex Vilenkin, as well as some earlier work by Sasaki-san and other people. And the basic idea here is that in the it is quite motivated from the top-down perspective that, again, you'll have many scalars in your model and so on, and so that your potential is complicated and you're in the multi-field inflationary scenario. And then you can imagine that in a wide class of models, your potential is complicated in such a way that you have many vacua. And so during inflation, you can tunnel to different vacua, and there will be bubbles, vacuum bubbles that are expanding. Now, the bubbles are expanding and later recollapsing. And from the outside perspective, they look like black holes. But some bubbles, they can become so big before collapsing that in fact they support inflation and a very non-trivial space-time multiverse structure inside, and this is where this comes from, the multiverse, so to speak, play on words. But from the outside perspective, it doesn't matter what happens inside. Everything looks like a black hole. But since the bubbles can be distributed in size depending on when they formed, you'll have a broad distribution of PBH. Now, as discussed in this study with Sasaki, Alex Kusenko, Takada-san, and other people, we revisited this scenario, and here's a sample potential, a two-field potential, just to illustrate how this could be possible. So this is a tilted Mexican hat. So you start on top, you roll in the rim. Now, as you pass right here in the middle, you tunnel, and you create vacuum bubbles, but then the tunneling shuts off as you roll down. And so now you have a bunch of PBHs resulting from this. And this is just a toy schematic. Now, in fact, such a general scenario might have already been detected by HSC. And this is very exciting. So let me tell you about this. Let me remind you that, as I mentioned to you earlier, the microlensing constraint on the PBH, this actually turns out to be very interesting. In fact, Subaru HyperSuPrimeChem, which IPMU is actually leading these efforts, they are looking at the Andromeda galaxy, and they found a very interesting microlensing, actually, candidate event. And this is reported in this Nature paper from 2 years ago. And Takada-san, he's the lead person on the HSC team, and he's also co-author on the study. And what is very interesting is that this very broad mass distribution from this general scenario bubble multiverse, which is this line right here, it is consistent with the HSC candidate event right here and accounts for all of dark matter. So this is a very exciting possibility. And in fact, one can do a little bit more. If one can generalize the model, one can simultaneously observe a variety of observables beyond just dark matter HSC. In particular, in a generalization of this model of formation, you can have a more complicated shape like this and simultaneously explain dark matter, HSC, LIGO events, and seeds of supermassive black holes. And HSC actually has finished collecting recently more data, and we are very excited for the new release of the analysis. But as they will push down right here, they will be able to definitively test if this general possibility can account for all dark matter or not in this open parameter space. So let me just mention also another interesting feature of this possibility is that while earlier one of the early questions that we started with was, of course, how do you peak in this open parameter space? And one possibility was to look for observables from small PBHs being captured to neutron stars and destructing them. Well, another possibility is to look for the tail of a distribution that sits inside this open region. Okay. So let me summarize. This is now a Renaissance era in PBH research. And of course, a lot of this has to do with the synergy with the multi-mesh synergy astronomy. And again, a lot of very exciting work that is being done by N3AS members. And PBH is very exciting in the sense a standard model dark matter candidate, and there's deep connections with a variety of puzzles, such as seeds of supermassive black holes or the R-process nucleosynthesis, which I mentioned. And of course, in the future, we aim to make more definitive statements about the general role of PBH and how it relates to dark matter. Thank you very much.
Okay, thanks Volodymyr for the interesting talk. So are there any questions or comments for Volodymyr today? Okay, George.
Yeah, thank you, Volodymyr. Very nice. So a question on the 2019 Nature paper candidate event from HSC, from Hyper Supreme Can. So what are the other possibilities for that? Is that, you know, I mean, there are systematic issues, right? So could that be a variable star?
Well, so my understanding is that so the plot right here, so this is right here is what is being seen. So I think this is the reference, and this is the target that is being subtracted, and then this is the fit for the light curve. And the event is right here, and this diffraction, the event right here corresponds to, once you have this candidate, you also take into account the dark matter distribution and so on, and then you can make this type of plot on the right. So
I'm just asking what else?
Yeah,
what could
I suppose in principle there could be some mimicker, but I'm not sure this is likely because yeah, I'm not sure this is likely.
Okay, and then looking at your purple band there, that's really interesting. So that purple band on that slide on the right hand figure, that's what's allowed by HSC's observations. Is that right?
Yeah, this is within the uncertainty. Yeah.
So they're only allowing you know, all of the dark matter or some significant fraction of it to be. You know, the only way that could be consistent with HSC's observations is if it's really light PBHs, right? 10 to the minus 14 solar masses or lighter.
That's right.
Okay, thank you.
I mean, of course. I mean, another, but I mean, of course, you can always do so in the general formation scenarios, you usually have a delta function like shape. And I mean, of course, you can try to fit the delta function to this or some other shape. But if you want to explain with this general scenario all of dark matter, then the tail will be hitting the HSC right here.
But that conclusion that you know, that purple band is for some fraction of dark matter in one mass, right? So in other words, if there's a distribution of masses, you could have a higher fraction of the dark matter be primordial holes. Is that right?
Yeah. So well, so with this line right here, you explain all of dark matter, right? So maybe this plot is not so clear, but let me just explain. So you take this distribution, right, and you integrate over this bin, for example, and then you ask, well, do I get one event or not? So this is basically how this plot is made. And with this line, you account for the one event, and you also get all of dark matter. Now, if you have some other shapes, then yeah, you can have different kinds of possibilities.
Okay, thank you.
Okay, so any other questions or comments? Okay, so I have a question. So you mentioned that just like the primordial black holes could be possibly the upper size. So I'm wondering, do you have estimates for the mass of the neutron-rich material that could be ejected from this scenario?
Yeah, thank you for the very interesting question. So, yeah, so in this study with George, this was analytic study, so we estimated of quite a sizable amount between 0.1 and 0.5 solar masses, but this is a little bit optimistic. But even if simulations show that you get a little bit less, this would still be great.
Okay, got it. Yeah, that's a lot. Thank you.
Yeah.
So
I know you can show, Radice's simulations.
Oh, okay. So what will be like, I don't know, what is like the estimate like ejected velocities for this material to be ejected away, like 0.1c, 0.2c? Do you have some estimates?
I do have some estimates, but I do not have them right now. Yeah,
Okay.
but this is actually exactly how this is made. So the way the estimates were done to get this amount was that in the equator, since the star is spinning very fast, so this is a millisecond pulsar. Since you're spinning very fast, the stuff in the equator is almost at the mass shedding limit. So at some point it will be flying out. So you can estimate how much stuff overcomes the ejected velocity. So, but I don't have these numbers right now.
Okay, thank you.
And as George alluded to, let me just mention that David Radice, who's our collaborator for the 511 kV study, he had some interesting preliminary simulations, and he, which I don't have right here, but he also has some interesting code that will hopefully recently show some very cool results and hopefully confirm some of the stuff.
Yeah, in what he in his simulations, it's really the shocks that are generated by these high-speed primordial black holes that really help with the ejection of material.
Okay.
The hole is falling in, this tiny hole is falling into a deep gravitational potential well. So it's moving pretty fast when it hits that nuclear matter wall. And there are shock waves as it, as a shock that forms as the PBH moves through the nuclear matter.
Okay, yeah, good to know. Okay, so are there any other questions or comments for Volodymyr today? Okay, I think I didn't see additional questions. Okay, so if not, let's thank Volodymyr again, and we will see you again after 2 weeks. Thank you, Volodymyr.
Thank you very much for the opportunity.